about heat capacity. The heat transferred to a system appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transferred. Q equals to coefficient multiplied by delta T. The magnitude of the coefficient depends on the size, composition and nature of the system. We can also write it as Q equals to C delta T. The coefficient C is called the heat capacity. Molar heat capacity. The molar heat capacity of a substance Cm equals to C by N is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius or 1 Kelvin. Specific heat capacity. Specific heat capacity is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius or 1 Kelvin. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance C by the mass m and temperatures change delta T as Q equals to C multiplied by m multiplied by delta T. The relationship between Cp and Cv for an ideal gas. At constant volume, the heat capacity C is denoted by Cv, and at constant pressure, this is denoted by Cp. We can write equation for heat Q at constant volume as Qv equals to Cv delta T equals to delta U, at constant pressure as Qp equals to Cp delta T equals to delta H. The difference between Cp and Cv can be derived for an ideal gas as: for a mole of an ideal gas, delta H equals to delta U plus delta Pv equals to delta U plus delta RT equals to delta U plus R delta T. On putting the values of delta H and delta U, we have Cp delta T equals to Cv delta T plus R delta T. Cp equals to Cv plus R. Cp minus Cv equals to R.